Okay, so about the
Yeah.
telescope loan program, please, utilize the scopes. I'll send out an email reminding you of what we have and how we'll offer instruction for them. Bruce, did you send out your thing about the Lake Sylvia? Yeah. Right. All right, but I do want to, March 22nd at Lake Sylvia, we're doing a public star party. And of course, all our club members are welcome. We were talking about the idea of maybe, was it Saturday night is the public star party, perhaps having a CAAS only event Friday night, having a barbecue out there and an observing event. So we'll give you further information about that. All right. So I'm going to turn the meeting over to Rocky, our program director, and he'll introduce our speakers tonight.
I don't think, do we have the video? Okay, no video tonight of us, so but you'll get to see the presentations. Anyway, our first presentation is the Elusive red dwarf stars, and they're pretty. I've been doing a solar neighborhood program, working on it for about a couple of years now, and almost all of them are red dwarfs because those are the closest stars to us. I mean, there's some other ones like Sirius and Procyon that aren't red dwarfs that are close to us, but most of them are red dwarfs. And anyway, Jim Sykes is going to give us a presentation on that.
Other way. This way.
About technology here. How's that? So, can you hear me? Okay. We will be talking about the red dwarf stars, which, although there are a lot of them, you can't see them with your naked eye. The very brightest there is in microscopia and is mag 6.7. So unless you are really, really good with your eyes, I don't think you'll be able to see it. I certainly wouldn't. That is the brightest one. Yeah. It's all downhill from there. Yeah. Okay. Before we go totally into the red dwarf thing, I'd like to do a little review, especially for the newer folks. Some of you seasoned hands will not have anything new here, so try not to snore. When we look at classifying stars, we generally do it by temperature. So you've got the letter designations O through M there, and O stars are hotter than 30,000 degrees. That's the surface of the star. B stars go from 10,000 to 30,000, and on down the line till we get to where we're going to be more interested in over here with the M class stars, where the red dwarfs mostly lie, and those are about 2,300 or 2,300 to 3,700, or maybe 4,000, depending on who you want to listen to. If you'll notice, we have a line of stars here, which is where most of them are, although we have some scattered down here, we have some scattered up there, and some over there. But most of them are here, and those are what are called the main sequence stars. Those are stars that fuse hydrogen at their core. So that's most of the stars in the sky. Then up here you have your giants and supergiants, and down here your white dwarfs. Just a little review of the classification system as to how we got where we are. That OBAFGKM is kind of strange. There's nothing in order there. But originally in 1890, Wilhelmina Fleming, working for Charles Pickering, did the first classification of stars, and it was mostly on the absorption lines of hydrogen and helium. So whatever was the most prominent got A, and then it went on down the line to P. And then in 1901, Annie Jump Cannon, also working for Pickering at Harvard, reorganized them on and combined a bunch of them and ordered them on temperature and spectral lines. Then, I don't show it here, but in 1911 and 1913, Hertzsprung and Russell did the famous Hertzsprung-Russell diagram we'll look at in a minute, which ordered them. But what we use now is basically the MK or Morgan-Keenan system, which took all those letter designations and broke them down into a finer structure. So instead of just O, you had O0 through O9. And the hottest was O, and then it cooled on down to O9, and then it went to the next level, and so on down the level. So then they also added Roman numerals because you have two. Let's say you have an M-class star. Well, it might be a main sequence star, or it might be a red giant. So they wanted to be able to differentiate that, so they use Roman numerals, starting with Roman numeral 1 for supergiant, and all the way down the line to 7 for white dwarfs, with the Roman numeral 5 or a V there being the main sequence stars. And officially, all main sequence stars are dwarfs in the classification system, although it's kind of hard to think of a big old O star as a dwarf, but they are. Then later on, when the brown dwarfs were discovered, which are not really stars, but almost stars, they added LT and Y down at the end of the diagram to be able to. Yes. There. Okay, right now smack. Okay, there we go. So anyway, yes, you're absolutely right. The mnemonics are there, and where we're going, you can see here. You got the hypergiants, supergiants, and so forth, and down in the white dwarfs, and you've got these letters, but the dwarfs actually get their own letter, that they're D. Clever, huh? Okay, so we're going to be interested in the area here where the red dwarfs, which are all main sequence stars. That is, they're fusing hydrogen. So here's kind of a fine structure of where we're looking at, kind of between 2300 degrees and 4000 degrees. That's Kelvin, basically Celsius, but starting at absolute zero. You can see there's Barnard star, Proxima Centauri, but there's where we're mostly looking. Some people bring them up into the Ks, maybe K5 or K7 on down, and maybe they might scooch it a little bit this way, but basically we're in the M class for most of the red dwarfs. Here's the fine structure I talked about, where they put the M's from 0 to 9. These are the hottest, these are the coolest. And you'll notice that the mass, these are mass in terms of the sun. So that's an M0 is 60% of the mass of the sun.
Hold her.
Hello? Okay. So moving on. You'll notice that the radius and the mass track pretty well, and the luminosity there, the brightest of the dwarfs are a little under 7 or 8% of the luminosity of the sun, and then way down here we're at around 100th of the luminosity of the sun. So they're not very bright stars. You can. That's the brightness. That's again of the sun, 1/10 to about 1/10,000th of the brightness of the sun. Pretty close. Remember, these are percentages here, so you got to add a couple of zeros. Yeah, so yeah, close. Yeah. So math is tough, right? Well, there you go. Okay, so yeah, there we go. Okay, so what we see in the night sky is kind of misleading. We see the bright stars. If we don't see many O's, of course, because there aren't many. B's 4 to 5%, and we see mostly these stars in main sequence. The K stars that we see, there's only a few of them that are main sequence, and most of them have moved off the main sequence into the subgiants, giants, and supergiants. So, and M's, the only M's we see are the red giants. So you don't see any of the as we mentioned before, the dwarfs. So here's what there are in the sky. You can compare it with what you see. There's not many O's, B's, A's, F's, G's, quite a few K's. Again, most of those we don't see. And then you have a whopping almost 80% of the red dwarf stars is what's up there. And these are the white dwarfs, the 5% there. And if you want to express it graphically, it looks like that, where the O stars are about half of one of those blocks, and then you move to the B, and so on down the line till you get to this big mass of red dwarf stars. Looking at the neighborhood, this shows a little past 6 light years. And you can see we got one yellow star there besides the sun, Alpha Centauri. Proxima and Barnard star are then the two red dwarfs, and these guys up here are brown dwarfs. So within 6 light years, we've got one yellow and two of the red dwarfs. Those are our neighbors. Looking at a size comparison here, got Earth down there, and then Jupiter, brown dwarfs, and this would be about an M5 red dwarf with about 15% of the mass of the sun, and then the sun. And this is probably a little better slide to show it. If you take Jupiter as one, then brown dwarfs are about 13 to 80% of the mass, or times the mass, sorry. Red dwarfs then go from about 80 to a little over 600 times the mass of Jupiter. The sun's a little over 1,000, and Earth's down there about 3 thousandths of the mass of Jupiter. Okay, so now, what makes a red dwarf star? There is no official designation for a red dwarf star. It's kind of depending on what you want it to be, but most people put it into spectral type M. A few people go into the late K stages. Mass about 7.5% to 50, maybe 60% of the sun. Surface temperature 2,300 to 4,000. And the convective nature is what drives these, is what makes these things really different. If you got 35 to 40% maybe solar mass, then the red dwarf, the star, is fully convective. It has a convective core, it has a convective envelope. That difference, say, from the sun, which has a radiative core, and you have to go out to about 70% of the radius to get into the convection. Evolution, they form just like all the other stars by accretion, only probably the cloud wasn't as big because you don't get quite as big a star out of it. Most of them are population 1. That's the stars in the galactic disk. They're the high metal stars. And when I say metal, anything beyond hydrogen and helium in a star is considered metal. So the population 3 were the original stars, just hydrogen and helium. Then you got your population 2, which are in the halos and the galactic bulge, and your population 1, which is in the disk, which is probably 80% of the red dwarf stars, and then the population 2 makes up the other 20%. They use the same fusion method that the sun does, proton-proton, where you get your 4 hydrogen. They say 4 hydrogen atoms makes a helium atom. Really, you get your 4 hydrogen atoms, which turn into your deuterium, which then pick up another 2 hydrogen atoms, turn into hydrogen 3. Then they combine, give you a helium, and you get 2 hydrogens and change. So then you start it all over again. So anyway, 4 start there, 6 start, and 2 with 2 left over. Energy distribution. The red dwarfs, well, we'll take a star like the sun, around 6,000 degrees at the surface, and most of the energy is in visible light. Invisible light, not invisible light. Okay. So as we cool down, the curve moves to the right, and by the time we get into the red dwarfs, not only is there a lot less energy, but the peak of the energy is out in the infrared. So when you look at a really cool red dwarf, you can see why you don't see much. They're hard to see, but of course, an infrared telescope like the Webb would do a pretty good job of it. Would probably the most interesting characteristic of a red dwarf is that they are flare stars. Most of them, when they're young especially, they're flare stars. And their X-ray and UV radiation can exceed that of the sun by, as it says, a factor of 10,000. So we're talking a lot of high energy here. What happens is, because of their fully convective, the magnetic lines coming up to the surface get really twisted and broken a lot, and when they recombine, there's a lot of energy there. So that's what makes the very strong radiation and strong coronal mass ejections. And it also causes large sunspots. Say the sun rarely would exceed 1% of the surface with sunspots, whereas a red dwarf could get 20% of the surface in sunspots. Now, as they age, they put off so much material, they tend to slow down and become less active. But especially when they're young, they're really active. The first one, AEX microscopium, we talked about, the brightest one, that's a flare star, and it varies about half a magnitude when it flares. So that's pretty lot of flaring. Okay, to no surprise, I guess, the evolution of a star is mass dependent. If we're down around 0.35, 0.4, the mass of the sun, where we have fully convective star, then hydrogen is transported out of the core and back in. You get a whole loop here. So unlike non-fully convective star, you don't run out of hydrogen in the core till all the hydrogen in the star is used up. So that means that when you add the fact that they're burning hydrogen very slow to the fact that they got the whole star of hydrogen to burn, it takes a long time for them to burn out. When you get heavier ones, between 0.4 and 0.5 maybe, it's mostly radiative in the core. And so here we can get, at the end, we can get hydrogen shell burning. And when you get hydrogen shell burning, the core is contracting, and the whole star kind of contracts then, and it heats up, and you get a blue dwarf out of it. The surface layers get hotter. Now, that's all theoretical, because these things take so long to do that the universe hasn't been here long enough for the first red dwarf to do that. So that's what their figures say anyway. Then later on, 0.5 to 0.8, if you get up around 0.6, 0.8, a lot of authorities don't consider those to be red dwarfs. They're kind of orange dwarfs maybe, or just low mass stars. But these are massive enough to get some helium burning at the core in their later stages. And they actually, it doesn't helium flash like you do in the bigger stars, but you do get some more gentle helium burning if gentle and helium fusion go together. And they can eventually become red giants. Then you look at the lives of them, that the bigger ones are on the main sequence, as you can see there, for 18 billion years. And all the way down to the bottom there, about 0.8 or 0.7, 08 or 075, the mass of the sun, 158 trillion years. Again, these are estimates, being the universe has been around only around 14 billion years. So we haven't had any red dwarf leave the main sequence yet. So what everybody wants to know is, are we going to find life on red dwarfs? Or can it be? Well, there's pros and cons, and so you can kind of make your own conclusions, but the pros are, well, there are a lot of them, right? And they last a long time. They seem to have a lot of planets, and the orbits seem to be more stable because of the low mass. But then the cons, if you get those radiation when they're flares when they're young, they can strip the atmosphere. You'd think they'd kill all the life, and you got to be close. Let's say the habitability zone, the Goldilocks zone, would probably, if you think about the sun, would probably be down around the orbit of Mercury or a little inside. They get tidally locked. If you think of how Jupiter squeezes Io, you could the red dwarf would squeeze the planet. Sunspots, and then there won't be any photosynthesis. So if you get life, it has to be something that doesn't depend on photosynthesis. As we know it, that's correct. Okay, if you want to go see these things, here is Proxima Centauri in this red circle. You look real careful, you can maybe see a little red dot there. If you have the Hubble telescope, though, it looks a lot better. So there's the characteristics of Proxima Centauri. I'll just let you read them there, but I will point out it's magnitude 11. And you're going to have to go somewhere besides Arkansas to see it because the declination's about minus 62 degrees. So probably want to pick a different one. But Barnard's star would be an interesting target. It's the next closest there, and magnitude 9.5. It moves fast. It's the fastest moving star of any that we can see in the sky. They're half the diameter of the moon in 87 years. So over a lifetime, that's pretty good. If you want to see it, it's up in Ophiuchus, and here's a little diagram of between 2015 and 2030 at 5-year increments, how far the star moves. So if you look at it over a couple of years and either photographic, in fact, I think in the solar neighborhood thing, they ask you to look at it a few months apart or maybe a year apart and draw it, and I think you'll be able to see that it actually moves. Here's one from Rocky. Took this picture of Wolf 359. 7.8 light years away, but it's quite a bit dimmer at magnitude 13.5. So you're going to have a pretty good scope and a pretty dark sky to see it. But it's in some of the literature mentions in the Star Trek saga there, the Battle of Wolf 359. For all you science fiction fans, it's also in a couple of books. The Ringo books I've read. I haven't read the McLeod book, but the name is interesting anyway. The picture, Rocky. I couldn't tell you. I don't know, but you could whichever Ken McLeod it is, he'd probably be happy for you to buy the book and find out. Okay, so anyway, the Solar Neighborhood Observation Program. If if you want to look at a bunch of these things, it has over 200 of the Class M stars that were within 10 parsecs, or about 32 light years of us. And says all objects are brighter than Mag 17, which is not all that bright. So for you, yeah, that's okay. So any questions? If not, thank you very much, and I'll leave you with that quote by Mr. Haldane, which
Well, this is our constellation of the month, and I know a lot of you have looked at a lot of stars, but I really like the winter skies because of the winter. You just got more bright stars there than you do any time of the year, and you can, of course, Orion's one of the is the brightest constellation. It's got 2 first magnitude stars and 5 second magnitude stars, and I'll show you a chart in a minute that shows how many how many stars are in bright stars are in the winter hexagon. So I said it's starring Orion the Hunter. When you're tracing out the winter hexagon, and my goal in this is to get people to go out and look at the stars. And I know we've got bad weather, like next week's supposed to be cold and rainy all week. But after that, the moon should be out of the sky, and maybe it'll get clear and warmer. First, there's, No, I didn't take it. I've taken one like that in the past, and you can get real nice colors just taking it with a regular DSLR. I'm sure that's what somebody did here, but I didn't take that. I took some of them in here, but not that one. And Jim was talking about, star colors in the Russell Hertzberg diagram. Well, almost all quite a few of the star colors are represented here in the winter hexagon in bright stars, and you can see Rigel is I don't know if it's not a class O, but it's a B, probably a B. Oh, that's right. Yeah, I remember that. So you've got some rare stars in Orion. Then Sirius, I think, is a white star, and the Sun and Capella, which I'll show you in a minute, are yellow. Aldebaran's orange, and Betelgeuse, of course, is red. And here's the winter hexagon, and the way you start is to start with Orion, and if you take the belt and go, oops, that wrong thing. Okay. Oh, thanks. And you take the belt stars and you trace them to the left, you find the brightest star in the sky, Sirius. You trace them to the right, you find red or orange Aldebaran. And Sirius, of course, is in Canis Major, Aldebaran's in Taurus. But then you can work on around and find Capella, Castor and Pollux, and Procyon, and there you've got the winter hexagon. And the constellations in it, once you locate the stars, it's pretty easy to trace out the bright constellations, because there's 6 bright constellations here too. You got Orion, which of course I talked about was bright, but also Taurus, which is very distinctive with its V, and it's the horns of the bull. And then you got the Pleiades over here on the side. Then you move up to Auriga, and it's bright stars making a pentagon. I think I left a star out there. And these 3 kids right here are kind of neat. And then Castor and Pollux, the twins, and they make a nice figure. It's more like a square but you can trace out and make it look like stick figures. And Canis Minor is real simple. It's just two stars, basically Procyon and Beta. Sirius has got 4 bright stars in it. All these are bright second magnitude stars, these 3, and then Sirius is the brightest star in the sky. And that's Canis Major. A couple other constellations are Monoceros, which has a lot of neat deep sky objects in it. It's a hard constellation kind of trace out, but it's easy to find. And then Lepus. Lepus is pretty easy to find right under, and it's kind of bright, right under Orion. Yeah, I've got a picture that shows the Milky Way here in a second. And here's the star chart. Dadgummit. I guess I didn't save it after I marked them, but I marked all the stars on another one. But Sirius, Capella, Rigel, Procyon, Betelgeuse, Aldebaran, Pollux, Hera, Castor, Bellatrix, and Elnath are all in this. So there's like, I think that's 11 stars out of the top 26 are in this area of the sky. So this is the brightest area of the sky. And this is just the whole thing. But there's another asterism. The winter hexagon is an asterism, and then an asterism is just a group of stars that makes a figure. Well, another asterism that's kind of famous in this and really easy to find is the winter triangle, and that's a equilateral triangle, and that's how you find Monoceros is in the middle of that triangle. That's the dark. See, everything else has some stars around it, but Monoceros, basically that's a vacant area of the sky almost. I'll point out the second magnitude stars. There's some more here that I didn't mention. These 2 are second magnitude. That's second magnitude, and I think that one is too. Plus the 3 in Canis Major. So there's a lot of bright stars here. And Orion has several parts to it. It's got a little bitty head, a club, and a shield beside the belt and the sword that we're all familiar with. And there's, of course, one of the most famous objects in the sky is the Great Orion Nebula. And that's actually M42 and M43. And then the trapezium's in the middle of it. And that's easy to find with binoculars. And that's when you go out, if you've got a pair of binoculars, there's a lot of really neat objects in the winter hexagon. A couple that are kind of telescopic are the Horsehead Nebula and Messier 78. Then we go to Taurus, and Taurus has the Hyades, which is you know what? I forget. That's about 140 light years away. I think the Pleiades are about 550, if I remember right. Yeah. And Aldebaran, which looks like it's part of the Hyades, is not in that cluster. It's closer, I think. I had all that written down, but oh well. So M45 has got a lot of nebulosity around the stars. And of course, that's the Seven Sisters. There's another one in it, M1, and that's the Crab Nebula, and that's, I think, a supernova remnant. Is that right? Then we've got Canis Major and Canis Minor, and Sirius is one of the closest stars. It's like 8.7 light years away, and then M41 is a very nice open cluster, very easy in binoculars. It might even be visible naked eye if you're in real dark skies. And Adhar is one of the top 25 bright stars. For Scion, I think that's like the 7th brightest star, and it's kind of a yellow star. Then Auriga has 3 bright Messier objects in it that are really easy with binoculars, 3 clusters, and this is just a nice region in here. But let me go back to Taurus. And Taurus has the horns of the bull, and Beta Auriga is the same as a star in Taurus, in both Taurus and Auriga. Now Auriga makes a nice pentagon, and there's the 3 clusters, M36, M37, and M38. Then we've got Gemini, which is very easy to find and see because of Castor and Pollux. And M35's a nice cluster, and in a telescope you can see this little open cluster over on the side of M35. And this time of year is a good time to look toward the north too. The Big Dipper is just coming up over the horizon, kind of like it shows in the chart here, and M81 and M82 are well placed for a telescope and binoculars. You can see those with binoculars. And then Cassiopeia is still up high in the northwest. Cepheus is still in the west. So I like this time of year because I remember when I was a kid being out, my mother planting the garden and being out there about dark and seeing the Big Dipper for one of the first things I saw. So if you don't know them, the way to learn them is to, and I sent out a copy of the star map, and so you can print it out. And it's also got a checklist there if you want to do a little scavenger hunt. But before you go out, start kind of committing a little map memory. Memorize the bright stars are the main thing I start with is learn the bright stars, and then from there you can after that you and so basically you learn the winter hexagon and the bright stars that go with it, and then you can start tracing out the constellations and memorize the constellations, and you can take it out and use a red LED if you do, and repeat it. Don't just go out there one night. Go out there 2 or 3 nights and rename the stars, trying to learn a few extra stars every night. And I think there's a lot of really good binocular objects, and the list that I sent has the ones that are good for binoculars. And here's my favorite binocular for this is a 8 by 42, and I've got the Bushnell. That's really a good binocular. And something that's also gotten a lot real popular, there's 2 kinds of binoculars. There's Poro Prism, which are the old-fashioned kind that are like that, and they have a prip, and then Roof Prism that are straight through, and they're a little lighter weight. They're more expensive, but they're lighter weight, and they also have a lot closer range. So they're better for butterfly and bird watching and stuff like that than the Poro Prism. So if you're going to do both, this Vector Crossfire is a very nice binocular. And like our library telescope program, they also have a library binocular program, and that's the binocular they use in the library binocular program. So if you're getting your first pair, I'd recommend 8 by 42 or 7 by 50. If you're older, 8 by 42 is better. If you're younger, got younger eyes, 7 by 50 works. Or you've got a a light cone that comes out. When you're young, you have bigger pupils than when you're old. As you get old, your pupils shrink. So if you got a so that, and I think's got, I should have 5, is it 6 or 5.2, 5.25, and that was like 7. So if you're older, that fits in the cone, so you can see all the light that's coming, but you lose a lot of light in that one. But that one magnitude one magnification, 8 to 7, sure makes a lot of difference to me. I started out and used 7x35 for years because I had an old pair from World War II, and 10x50s are good too. They require a little more stabilization. You have to hold them stiller. Leaning up against a car or a building or something like that's good. Or you can get a monopod now, and that has an adjustable top, and those are really good for something like that. It's amazing how much stabler they get when you can stick a monopod on the ground, and you can adjust the binocular to the height that you want to do it. If you get larger than 10x50, you'll need to put them on a tripod or some kind of a binocular stand. So, any questions? You know what? I had a slide in there for that, and I don't know where. I had a slide from Rhinoceros that had that in it. I guess I don't know what I happened to do it. You want me to go back to the hexagon? Yeah. 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 Oh, I got it listed wrong. I think that yeah, I think there might be a cluster there that's the 2263 maybe. But these all three are nice binocular objects, spectacular imaging or telescope, but really spectacular imaging, or EAA, right? I'm going to go back through here. Okay, how do I? There we go. I thought I had one on Rhinoceros in there. There it is. Okay, so there's the Christmas tree cluster in Cone Nebula in Rhinoceros, and the Rosette Nebula in cluster in Rhinoceros, and those are both great objects. Okay, that's all. Thank.
Well, as many of you know, I like to play around with 3D printing stuff. And I kind of get a fascination with anything that has to do with chronometers. There's several plans of different chronometers you can 3D print. And I ran across one for this thing. It's called a Guard Heliochronometer Sundial. And of course, John built a sundial out in the back over here that does essentially the same thing this thing does, tells time. The neat thing about this, this guy designed it for 3D printing based on a plan that was developed by a guy named J.D. Guard. He's some mechanical engineer out in Tucson, back in the 70s that built the thing out of brass and aluminum, apparently, and probably did a bunch of etching and everything else to make it real pretty. The thing that's neat about these sundials, this particular one is accurate to 5 minutes. If you use a vernier scale on the other end of it, you can get it down to 30-second accuracy. So it's probably one of the most accurate ones you can find. It's not some kind of digital thing or that you have to stand out in the sun and look against an outdoor scale. But I printed out some of the detail that you have to use to get it to work. You can just kind of browse through there and see there's several pictures of various sundials that have been built. It's kind of neat. The cool thing about this is that I found if my watch battery ever goes out, you just attach it to your wrist about like that. And it actually works kind of backward from a sextant that they use on board ships, because all the same principles. On this, it's got a dial for your particular latitude. For us, we're sitting at about 35 degrees. So you set your dial at 35. You have to level it, and I can print a base. Actually, they have bases that has bubble levels and compasses on it, so you can set it out and do all your leveling. It has little screw holes here where you can put in leveling pegs. I didn't do it because when I go out on my deck rail is pretty level, so I don't have to use the pegs. If I go anywhere else, I'd have to use pegs to make sure you can get a good level. You can use a compass off your phone to get your true north, and you point this end of it north. Then once you get it leveled and pointed north, your next object is to get this pointing at the sun. Of course, you're pointing south now. You have a hole in this end of it, and then you got your what do you call it, analemma scale on there. So once you're leveled, you just move this dial around until you get a dot showing up on the analemma scale in the correct month, and then you look down at the bottom dial down here, and that'll give you the time. And each one of these little ticks is 5 minutes. So you can get that. Well, then you have to adjust for where we are for local time. This is only standard time. So you want to get it for us. Well, my house is at 92.25 longitude, and time is based off 90 degrees. So every degree is about 4 minutes in time. So whatever I get here, I have to add about 9 minutes. And when I've done it, the doggone thing works out pretty good. So it's amazing how it works. The way the vernier scale works, you put it on this end and flop the two vertical parts. And vernier scales are kind of weird. I don't know if you've ever had to mess with them. When I had to read barometers, in my young days, and so that you could accurately set the aneroid barometers, they used vernier scales, and I was always screwing them up because you got to match up one line with another line, and by the time you get that done, yeah, well, slide rules are easy compared to vernier scales. But anyhow, that's the basis on how this thing works. And of course, when you're looking at some of the various sundials, they're all got some kind of basis that's very similar to that. So, but anyhow, okay, for the TV folks, we'll let them get a good look here. And you can follow it around if you want to, and we'll just pass it around and just look at it. John, did you ever get any details from those links I sent you that where you could build something like that? Yeah, the one thing about when you put the vernier scale on there, if you want to get that much accuracy out of it, you offset the vernier scale by whatever your difference is in your longitude. So you actually just move it over 9 minutes for me, and for us up here on the mountain, it'll be I think we're about 10 minutes difference. We're 92. What is it, Bruce? Is 92 and a half? That's what we're at. Somewhere it says. Well, if we can fire up the RRT and take a picture, it'll be in the header. It'd be 92. Seems like it's 92.35. Yeah. A tenth difference from what I have at my house. So. Yeah, it's 9 minutes, a little over 9 minutes.
Really nice. It's a cat's meow. And it runs, it's what Danny's got in his scope, except it's a bigger chip. It's the same, it's the full size, whereas his is a shrunken size, and and it will run on, instead of UBS, it downloads the data off of fiber optics. So it's really fast, and high QE and all that kind of stuff. It's a true 16-bit CMOS, native 16-bit CMOS. So there's none of this stacking routine that I think was the root of the problem. It seemed like a great idea to try to give you the dynamic range of a 16-bit chip using a 12-bit CMOS. You know, they transitioned from CCD to CMOS, and when they did, the CMOSs were all 12-bit. And so this was the great idea. Well, we'll just stack internally 16 frames, and that'll give us the same dynamic range. But it made it complicated, and it's never really worked well. Lee got what? How many exoplanet runs did you do? Off the RRT. So it got some, you know, we could get it to run from time to time, and it didn't do too badly when it did run. So we've got that new camera. Well, then that had to be it's got a much bigger field of view, so we had to have a new filter, and they've agreed to modify the filter wheel we had, and so the filters now are going to be 50 millimeters square, and all those have been ordered. So they say that they will ship the camera and the filter wheel back to us as soon as they've modified the filter wheel. And so maybe it won't be too long before we have that in place. And we're going to that. And Danny and I cleaned the scope today. And we will install this program called APCC for the mount, which will create a model so that mount then from now on will make up for all the little errors in how it's flexure and all these other things that are repeatable. It'll correct all those, and for atmospheric refraction. So it will point and track almost like you were guiding without any guiding. It's close. Many people are taking photographs without guiding with that system. So near future, the RT should be back up better than we ever thought it would be. Much. Yeah, much bigger, smaller pixels, bigger chip. That's the problem with the one downside to it is the pixels are really small, and we'll have to bend to what? Yeah, it's no big deal. The chip, I don't know. I think I don't know. I won't hazard a guess. Yeah. Well, uh, I can tell you this, a round 50 millimeter filter would cut off the corners. So, yeah, it's a good sized chip. Yeah, 50 millimeter square. Yeah. I think they've all been delivered except for the V filter. We got imaging filters and science filters. And we don't have any narrow bands. And we can't put as many filters in it as we used to. So we will have with BVRI and L and the three red, green, blue, we'll have two filter holes left. Huh? As soon as they get it modified, they're modifying the filter wheel, and as soon as they do that, it should be soon. Yeah. Well, because we've got bigger filters now. The original filter wheel had a carousel in it with a little for the bigger filters, so it'll go with this camera. Otherwise, would be obscuring. No, they're just going to modify it, put a new carousel in it, and make some other changes so it knows where it is, I guess. Yeah, should be nice.
The library display at Terry Library has a series of photos that I have that people here have taken, and I need more. If you'd like, I'm going to change the exhibit at the end of this month. It's going to run 2 months. Carl says we need more people pictures. I have some, but if you have some that are good too, I would love to make big prints, and then we can ultimately make smaller displays, get these off at different libraries around the city. People are enjoying them. Ed just left. I sent this picture to him, but so he didn't see it. He didn't see it. But and if you have anything, especially with a library telescope, have a real good picture of Alan. He's in front and center of the display, and well, it's about libraries. So appreciate anything you might send my way.
Okay, so I'm gonna, before I close the meeting, I was gonna ask, does anyone have any new business that they'd like to bring up? David, well, come on up.
Hello. I'd like for all to know that there's now in the clubhouse a 24-inch television that is there for the purpose of the astrophoto head people to be able to display some of their photographs for other club members to see and play show and tell and stuff. And there's a rumor that folks like Darcy might even use it for outreach stuff too. There's a thumb drive stuck in the side of that television, and I'll let the technical people figure out how it works properly. In other words, help yourself.
All right, any other new business that someone would like to bring up? No? Okay, with that, I'm going to close the meeting and look forward to seeing all of you next month. Good night.